In case you don't know DAQRI, DAQRI is making AR glasses for the industrial sector, and these are see-through glasses, so the user can still see the actual environment. And the use case is, for example, like in this picture, for a worker in a factory to augment his vision of the environment with additional information. So for instance, if you're maintaining a very complex machine or a complex turbine and you get extra information laid off on top of it to carry out the task more efficiently. And in order for that to work, there are a couple of things that need to happen in the pipeline. So first of all, it's also an inside-out tracking system, as was mentioned in the morning by the Monado talk today, which means you have a bunch of sensors connected to your tracking system. So usually you have something like a wide field camera or maybe multiple cameras, IMU, sensor data, and so on. And this tracking system is providing a 3D pose. So basically a translation and rotation that you can use to render your virtual augmentations for each eye. So it's basically tracking your head position in a virtual space. So the application is going to render new frames for the left and right eyes. And what usually happens is that you have another post-correction stage to hide the latency of the rendering, so you can still correct it for the newest motion information. So in that graph, if you think about the tracking system, it's actually a little bit confusing here because you would rather ask the tracking system for a pose than just getting a pose from the tracking system itself. And the compositor that carries out the warping, the late correction of a frame, asks the tracking system for a newer pose than has been used for rendering this frame. And that allows the algorithm to shift the frame in simple cases or correct the frame for the newest motion information. Then eventually this frame is being sent to the displays. The display emit the photons reaching the user's eye. And there's a very important characteristic of an AR system, and that's the motion to photon latency. And by using this compositor stage between the app and the actual scan out, you can reduce the effective motion to photon latency from the point of the compositor up to the displays. So there are two things that are really important here for the rest of the talk. The one is, and that was mentioned before a couple of times, is doing things as close to scan out as possible, being able to execute the GPU warping step as close to the actual time when the frame is being scanned out. And the second one is knowing about the presentation of the buffer, because you don't just ask the tracking system for the most recent post that is available, but you actually ask it to predict a little bit into the future. So, you render a frame that is known to be shown at a particular time. And I created 3 videos with our glasses in preparation for the conference to showing you a little bit what the effect of latency actually is for the user. So in this scene, you see we're filming through our headset and onto an image target. And that image target is used to register a pose in 3D space. And around that image target, we render a wide rectangle. And this is the only virtual augmentation that's seen. The rest is really just the actual environment. So if you have a system with a high latency, you can see that the augmentation really lags behind. Quite a lot, actually. And for our system, this is actually what we had like 1.5 years ago, I would say. And adding this compositor stage, we were able to reduce the motion to photon latency, which you'll see in the second video, which fits now much better, but it's still not really perfect. Like you can see the color breakup is a little bit reduced, and the overall registration error. So the amount of the rectangle not fitting the actual world has also been reduced. But both of these modes are not using prediction. And because we're already quite late here, or close to the scan out, we only need to predict a little bit into the future, and that works actually quite well. So using the low latency mode with prediction actually shows you that the rectangle is now much nicer aligned. You'll also see a little bit of ringing at the end. That's where the prediction gets a little bit confused because it's quite a sudden stop. But most people don't stop that suddenly with their head. So it's actually, in practice, it's working out quite well. So much about the background here, and now I'd like to speak more specifically about the compositor that we built for our AR platform. So last year at XDC, I showed a short demo, basically showcasing how different latencies would impact your experience. But at the time, we were still basically running a desktop graphics stack. So we had the X server, we had some weirdly configured compos on top of that, and really no control about presentation time whatsoever. So what we started about a year ago was to build a KMS-based, our own small AR compositor, which is very much focused on our hardware and this use case. So the problem scope is actually quite well defined. And this slide here should give you an overview of the environment. So the compositor only runs on an Intel Skylake hardware, so it was very easy to use the existing open source driver stack. And on the user space side, we had to support OpenGL because most apps that we had to support were written in OpenGL. Like, we didn't want to rewrite that. But we also use OpenGL on the compositor side because all the presentation bits are really done directly with KMS. So all the EGL contexts and so on that we use are just surfaceless, and we handle basically the swap chain explicitly by tracking all the GBM buffers and so forth. And I'd like to go through a little bit how the applications talk to the compositor and the actual protocol. So this slide you really need to read from the top to the bottom. So it's this is the application's main thread opening up. Hope it's big enough. Yeah, should be. And once the application starts, it needs to set up a layer. That's really just our concept of a layer, and we made it easy. A layer maps directly to a hardware plane. Like just as Keith mentioned before, that we don't need to composite a lot of things because we basically have only one app that is running, and we might have a few overlays for notifications, but those are not really that critical, and it's enough to have a dedicated plane for this. So there's a dbus high-level protocol for this layer setup, and the application talks to the compositor running in a separate process over that dbus protocol, basically asking about, I want to acquire a specific layer. And that could either be the main one or an overlay layer. That's it. In response, the compositor is providing the dimension, the DRM formats and modifiers that can be used for that layer or should be used. And the application is, with that information allocating the GBM buffers, setting up the EGL context, and making sure the DMA buff handles are ready, and so on. Basically setting up a swap chain. And after that, tells the compositor in a setup layer call which buffers had been allocated, which modifiers had been chosen, for how many buffers and how many swap chains. And at this point, if the compositor is happy with that, it returns the application an opened socket, basically one end of a simple AF Unix socket pair. And from that point on, for all per frame operations, the communication happens over that socket, so not dbus anymore, because there might be some funny latencies involved with that. And the application's main loop is really just pulling on that socket and waiting for a command from the compositor to begin a frame. And this is really the point where the app application's render rate is limited and paced. And the compositor has full control of waking up the app and telling the app to render at to render a frame for a specific presentation time. And also all timestamps here are relative to a monotonic clock, which is very nice to have a common reference, because now we can just ask the tracking system and say, hey, we want a pose for that particular presentation timestamp. And at this point, the tracking system has to predict for quite a lot into the future. And this is still necessary because downstream, the error to correct is going to get smaller if the prediction was at least close to being right. So yeah, application asks for a 3D pose for the predicted head pose, and then basically binds the target for a specific index in the swap chain. So that's using EGL, basically the OES image extension. It's a little bit messy because you basically have to import the DMA buffer into an EGL image and then bind that EGL image to a texture and bind that texture to a frame buffer, but it actually works out quite well. And the app renders the views for that particular pose using OpenGL. And after rendering, we don't want to wait for the rendering here to finish. So what we do is we just create an EGL fence. So it's actually an EGL sync object. And export that to a DMA fence handle. And all that information is wrapped up into a new message that is being sent over this opened socket back to the compositor. So the app submits the frame back to the compositor, re-enters the loop, and goes back to sleep until it needs to be woken up again. On the compositor side, this is now running in a separate process. And there are two threads where one is basically just a simple control thread that handles all the dbus messages, tracks client state and liveliness and so on. And the other one is the actual presentation thread. And when that thread starts up for this first time, it needs to do the whole KMS setup, iterating the CRTCs, building up the whole chain, setting up EGL contexts, and allocating the buffer for its own small swap chain for the warping step. Because the warping, the GPU warping in that case is, of course, its own rendering operation. And in between those two threads, there's a small control message protocol, but that's not important here. And the main loop of the compositor is basically, it's also very simple, event-driven, by polling over a set of file descriptors. The first one is the other end of the socket pair to which the app is connected for each layer. So basically for each layer, the compositor, whenever there's a submit frame, so the result of an application's render operation coming in, this is just stored as the last submission of that layer. Then there is a timer for the warping, so that's a timer FD handle. And whenever the warping timer wakes up, the warping operation is being executed. And in that case, so on our system, we only do the warping for the primary plane because the notifications really, they don't need to be warped anyway. So that makes it a little bit simpler. So we check for the primary plane's last submission, and at this point, this is executed. It's scheduled quite tightly with the flip event. So we really want to make sure we check if the render operation from the application is actually done. Has the fence, the render completion fence, been signaled? And if it had been signaled, we take that one. And if it hadn't been signaled, we take the last one that we knew finished. And the idea behind that is that we'd rather rewarp an old frame than running into the risk of a currently in-flight render operation not making it. Of course, that's only really useful if you have GPU preemption, and to be honest, we haven't really gotten that far to really see how well that works on the Intel driver, but yeah, that would be one of the next steps. The warping algorithm, of course, needs a new pose. So as the compositor is directly connected with the display subsystem, it has a good idea, or at least a good guess about the next frame timestamp, and asks the tracking system to predict another pose for this for the next display time or next frame timestamp. And then the warping algorithm takes as an input the buffer that had been rendered by the application, the pose that was used to render that application's buffer, and the newest pose it just got. And basically the delta, or not really the delta, but by having these two poses available, the amount of correction can be calculated. And in the simplest case, that's just a 2D offset, and that works surprisingly well. Of course, there are more complex warping that you can do. And in our case, on the GPU side, we also do display distortion correction, as the physical displays on the sides are not have some physical distortions, and we basically invert those, which results in a better aligned content. And as a result of the warping operation, the compositor just sets the KMS plane properties, the frame buffer ID of the warped buffer, and also setting the infence file descriptor of the completion fence of the warping operation to make sure that the warping is done before scanning it out. Of course, hopefully it's done, because then we would drop a frame otherwise. There is another timer, which is the commit timer. It's a little bit awkward, because actually it would be nice if we just committed right after setting the plane properties. But as Keith also mentioned in the previous talk, once it's committed, I can't commit anything new for that plane. And there might be also an overlay plane coming in. So the commit timer is even more tightly scheduled to the flip event. So that's the atomic KMS commit. And basically, when that fires, we just commit the assembled properties and the assembled KMS state. Last but not least, there's the KMS device node itself, which will fire with the flip complete DRM event, and also providing a timestamp. I'm going to get to that a little bit later. But this is basically telling us that the KMS is done with one frame and is going to start out a next frame. So that's a good point in time to schedule our operations for the upcoming frame. And there are a bunch of timestamps that are being calculated here. So basically, we forecast the next frame timestamp to be this event timestamp plus the refresh interval. And relative to that next frame timestamp, we schedule the warping to happen a little bit before that, and schedule the KMS commit to happen a little bit after the warping. But that's all relative to the next frame timestamp. And finally, all the connected layers are getting a begin frame message where the presentation timestamp is set to the next frame timestamp. And in this case, we don't expect the application to render a lot of frames ahead. So it's really just this one frame duration, this one window where we expect the app to render. Right, and this is going to wake up the application here and producing a new frame, submitting the buffer, and so on. All right. Now, about that timestamp, while working on that compositor and debugging it, I was a little bit confused what that timestamp actually means. And thankfully, when I went on IRC, thanks Daniel Fetter is somewhere, I got a really good explanation of that. And it turns out it turns out it's actually confusing, but I now understand better why. So it turns out the drivers have this notion of high precision timestamps, which on the kernel side means there's this get vblank timestamp function that needs to be implemented. And also Keith mentioned it in his previous talk. Apparently that goes back, the semantics of the timestamp go back to the OML sync control extension, which says this is the timestamp the first scan line of the display begins passing through the video output port. So it's actually the time, if I'm not mistaken, immediately after the vblank. And that's kind of important to know because sometimes you have really weird displays with very, yeah. So there's actually a graph for that. So if that's sort of a high-level view of the vertical video signal, you have the blank interval that has a front porch, sync interval, and back porch. And here, this is the timestamp you get with that DRM event. And now, of course, in our system, we're interested in actual presentation time. And I mean the actual presentation time, so the physical photons going out, of course, depend now on the physical display properties. So let's say you have a rolling exposure display, then you might want to take the middle of that active video data region. But it really depends on the display and what happens downstream. In any case, it's important to know that you have that you know about this reference, because there might be displays that have a very large front porch out of some reasons, and then the offset between where this timestamp is and where you think it might be, which is when the event actually fires, the CPU time of when the event fires, the difference between those timestamps might be larger than you think. All right. So what's really missing from a user's point of view is this knowledge, whether or not the driver supports these high precision timestamps or not. I guess that could just be a simple property. The information is all there anyway. And documentation of these timestamp semantics, because really this the semantics and the reference to OML sync control, you only get that if you look at the kernel code. And secondly, so far I've only tested that with Intel hardware. So even though the documentation of get vblank timestamp tells you about the semantics of the timestamp, are all drivers actually implementing it like that? Well, okay. Right, then that's something, if that's going into official documentation, would be great if the semantics were actually fixed. Right, and the second part, which is kind of important, is executing very late KMS commits. And I guess, I mean, it's kind of an artifact of not being able to commit multiple times. From our point of view, with what we had to work with, to optimize the latency, we really want to commit the state as close to the page flip as possible. And in our case, that inherently means we can execute a GPU warping as late as possible. You can change the plane properties once they're committed, otherwise you get a busy error. And with that restriction, what is actually the latest point in time we can commit for a frame? And there's not really a good answer. I think so what we did, and I think what other compositors are also doing, is, so in this graph, the point B is the time when you get the DRM event, and basically the last point commit is sometime before that. In our case, we calculate this timestamp, so the next time we want to perform a late commit is basically the timestamp from the page flip event, that's C, plus the refresh duration, minus some fixed margin. And that's just hard-coded and something that we found works out quite well. And we're using the timestamp of C here, as this is less subject to schedule jitter, as that's hardware corrected and has, as I mentioned before, this particular notion of it's fixed to the scan out signal. Yeah, that worked out quite well for us. Of course, it might get more complicated when you have, and this is a little bit, to be honest, I don't know exactly how the variable refresh rates work But from what I read in the kernel documentation and from some discussions in IRC, what I understand is that there's the front port is basically dynamically extended until the display hardware has to present a frame. And in that context, what's the latest point to perform a commit here? And it's probably some time before the DRM event as well. But yeah, that's definitely interesting how that relates with reliable refresh rates. So the problem here is really, in summary, that this margin to schedule ahead is not really defined, so you just have to play around with that a little bit. And as also mentioned by Keith before, we only know this margin is too small after the fact of having dropped a frame. And a single dropped frame is surprisingly annoying with an AR headset. It's actually even more annoying when a previous frame is shown again. It would be better to just show nothing. But as the brain is, it's easier for the brain to interpolate different signals if it's not repeated, because otherwise you get this a very jagged motion. So the question is here, what can be done to make this better? And I think some suggestions had been made in the previous talk. Another thing I want to mention here is, since I was playing around with the VBlank timestamps, I thought it would be nice to visualize them, and we had a few discussions on the GPU-Viz project. And the way I've been implemented it is just to simply extend the DRM VBlank trace point to now carry this high precision timestamp. And I also extended GPU-Viz to optionally use that timestamp to show the VBlank markers. One thing to mention here is GPU-Viz is using ftrace under the hood. And if you want to use this feature, you have to make sure to set the tracing clock to monotonic clock. Otherwise, we can't relate to timestamps. And visually, it looks like this. So that's a trace of simple application. And you can see here that in that application, we also schedule the rendering quite close to the VBlank event. And let me see if that works. Yes. You can see that the DRM VBlank event now has additional, the trace point has additional data. There's a time field here, which is the absolute monotonic clock timestamp, and a Boolean that will tell you whether or not this is a high precision timestamp. And yeah, scan in a little bit, zoom in a little bit here. There are other things that are also visualized here. So this one point here is the render completion fence. This event, it's almost overlapping with the VBlank event, is the time of the KMS, when the KMS output fence was signaled. So when you do a KMS commit, you can basically give it a fence that should be signaled when the commit becomes active, and that's the timestamp you see here. This is using another feature that's now new in GPU-Viz, that you see this little asterisk here, which means the actual point in the timeline here is determined by an external timestamp that you can provide from the application. Because there you already have access to the fence and the fence timestamp, and you don't want to and you want to show this event exactly where the timestamp from the at the timestamp of the fence you got, and not at the time when you recorded in your application. Going back to the VBlank event, there's now a new option here to use high precision hardware VBlank timestamps, and if you turn it on, you can see that this purple line jumps back. So basically, the difference here is that this is when the trace point fired, but this is where, according to this OML sync extension, the first line, visible line, actually went through the video output. And it's kind of nice that you can now relate those things in GPU-Viz as well. And I think it's already been merged upstream. Right. So much about that. And there's another project I want to mention, and that's KMS quads. So when we wanted to start working on this compositor project, and our compositor code base is closed source, as it's very tightly related to the tracking system and so on. And at the time, it wasn't possible to make that open source. But we initially had a good idea what technologies to use and what parts of the open source driver stack to use. But it's one thing to roughly know what you want to use and another thing to have actual working code. So what we did is we worked together with Collabora and basically had them write a nicely documented, simple KMS sample that is somewhat lean towards our use case and made that open source from the very beginning, because it was a really good way for us to learn their APIs in the right way. It was a good way to have a communication platform without necessarily making our whole compositor project open source, which is anyways kind of targeted at our specific hardware. So the use for the community is not that, there's not so much use there. So KMS quads is straightforward and well-documented KMS example. As I mentioned initially, Daniel from Collabora started that work. It really helped us to get our specific compositor work done much, much quicker. And we also made sure to have bugs that we might have found when we adopted the code, make sure that we create merge requests on the open source sample project. We had other people contributing, which was great. And some of the lessons learned and features we've been using on our side also went back into this open source project. It's MIT licensed, and there's a link here in the slides. It's on the free desktop GitLab instance. And what it does, it really shows and explains with lots of comments in there how to use atomic KMS for page flipping, how to set up the whole GBM buffer chain and use OpenGL Core or ES3 and as a fallback ES2 together with EGL to render into these buffers, how to use the DRM format modifiers. There's a little bit of this presentation timing and scheduling also in there. I think it's currently still a merge request, but it's up there. And finally, use with DMA fences, use of DMA fences via EGL sync is also in that sample. And it uses optionally login-D to switch to virtual terminal and open the devices, so it's kind of nice to use as it doesn't screw up your system too badly if it crashes. Right, there are a few other smaller upstream collaboration that we did along this project. There are some OpenGL ES extensions that we wanted to use in OpenGL Core. So there's one new extension, DLX EGL Sync, which allows you to use EGL Sync objects in GL Core as well. And another one was to use the frame buffer flip Y extension in GL Core, which is something that's necessary if you manage swap chains explicitly with OpenGL because of the conflict of the different coordinate systems. Other than that, we also worked quite a bit with the Intel open source driver team. Like really, these are really small things that are were mostly trivial to fix, but on the product side, it really helps a lot if you get a patch within hours. It's makes really such a huge difference. And there was a regression in alpha compositing of CCS compressed surfaces that has been fixed. And another one which was kind of interesting for latency is that the page flip task in KMS run on a generic system worker queue in the kernel. And unfortunately, that task did not preempt other running user tasks. So whenever we had our tracking algorithm, for example, running across the VBlank boundary, suddenly the flip didn't make it because it didn't preempt our tracking system, but it should. And so that was a really simple patch. to make sure the page flip task runs now in a higher priority queue. In conclusion, for us, it was a really great time to start this project because really everything was there. KMS worked out great to implement a very lightweight AR compositor. It's not a lot of code, and we're very happy how this with the result of it. And there are a few things that would be interesting to fix. The timestamp semantics of the KMS events, of the DRM events, are somewhat undefined and would be important for any XR use case, really, to make sure this is accurate and well-defined. And secondly, these late commits from user space are somewhat tricky, but having seen Keith's talk just before, there might be better solutions coming up for that than trying to make this late commit stuff more well-defined. All right. Special thanks to the X Foundation for sponsoring my trip. Thank you. And also to Daniel Stone and Scott Anderson from Collabora, which really helped a lot, also with the KMS quad sample code. And Daniel Vetter for being very, very patient about answering lots of my confusing questions about timestamps and so on. That's it. Are there any questions?
Yeah, I was wondering if you had so right now you have a fixed delay before VBlank to start the GL operations in general. I was wondering if you have experimented with having a kind of adaptive thing which tries to reduce, and as soon as it drops a frame, it knows that I need to do a little bit to let a little bit more delay before. So have you tried something like this?
No, we haven't, but it would have been on the roadmap for sure.
Okay, cool. Yeah, we're pretty interested too for compositors in general. Yeah, cool.
No? Now is it on? It does. It turned green. That's fantastic. You talked about changing the pose time to be represented by the middle of the frame. Have you thought about adaptively changing the transformation of the pose data so that you have the pose for the top of the screen different from the pose of the bottom of the screen?
Yes. It's something I haven't mentioned is that the display, our current display is color sequential and global exposure, which means there's a very short time of the pixels lighting up all at once. It's an LCOS display. So, and that there's a very specific time that we can estimate for that. But we had thoughts about how to adapt it for a rolling exposure display, and there were some ideas about maybe doing some scanline racing. But I think probably predicting for different times at the top and the bottom would probably be enough.
That works surprisingly well. Yeah. But you say you're color sequential, so you actually have different pose times for each color?
Yes.
Wow.
Oh, by the way, I brought the device with me, and I'm more than happy to demo things and show you different latencies and the compositor running in action.
So thanks for the great presentation. You talked about the VBlank timestamps and the page flip event timestamps. So now you have the high precision timestamps that indicate, the first line of the next frame, and then that's obviously off from the VBlank timestamps. So did you compare that with the page flip timestamps? Because that should the page flip timestamp is what you should be using as the right event for when the next frame actually, flipped. Because the page flips might not happen for every VBlank. Like VBlank will be for every frame, but then in the kernel we also check if the blanking time is enough to do all the the register updates and everything. And if it's not, then it's going to actually delay it to the next VBlank. So, and then you won't get any page flip events in that case. So,
well, we're using the page flip timestamp, but the page flip timestamp has already been corrected for the first line. That was my understanding.
yes, yeah, so you should be, I guess my comment was that you should be looking at the page flip timestamp, and then the VBlank would just be for every.
We only look at the page flip
Page flip,
timestamp,
okay.
so we're not looking at VBlank events, actually.
Okay, good, yeah,
Yeah.
cool. Thanks.
All right. Thank you very much. Enjoy your lunch.